Hi, I'm Fernando Pereira from the Federal University of Minas Gerais in Brazil. In the last class, we heard about the worklist algorithm. In this class, we will see how you can make it run even faster by exploring different orderings in which constraints are evaluated. If you recall, the key to making the worklist algorithm work was to represent the constraints as a graph. Can you build a dependence graph for this constraint system on the left? There we go. This is the dependence graph. We are representing each constraint by the variable that it defines. That works because each constraint finds a single variable. So we will add this constraint to the worklist and then start solving them. Do you remember? We take a constraint out, evaluate it. If anything changes, we put the dependencies back into the worklist. However, thus far, we are assuming that we are piling up the constraints in this worklist in some random order. But it's possible to make the algorithm to converge faster if we use some particular ordering. Can you think about what would be a good ordering? Well, if we could sort the constraints topologically, that would be good, for we could evaluate the constraints in this ordering. Once we solve a constraint, we would know that whatever set that constraint defined would never be inserted in the worklist again. However, the dependence graph is not acyclic, so it does not have a topological ordering. However, we could find an ordering that's almost topological. It's not really topological, but almost. Can you think about any way to derive this quasi-ordering? Compilers typically use an ordering called reverse post-order. That's the ordering that we get after traversing the graph using that first search, in the reverse order. I'm showing you the code of that first search. Let me call it DFS for short. Perhaps you could take a look into this algorithm. It's pretty straightforward. Basically, when we have to visit the neighbors of a vertex, we pile these neighbors up in a stack. Then we visit the nodes according to their position in the stack. That's simple, traditional DFS. But we keep a counter. We started with the number of nodes in the graph. Whenever we are done visiting some node, we assign the current counter to this node, and then we decrement the counter. The DFS traversal sort of creates a tree on the graph, a spanning tree. The reverse post-order sorts this tree topologically. For instance, let's try to apply reverse post-order in this graph. On the right, you can see the tree that we would obtain using DFS. Notice that more than one tree can exist for the same graph. Anyways, the numbers next to each label gives us the reverse post-order. So the last node would be x5 and the first would be x1. But we still need to revisit the worklist algorithm to adapt it to use our reverse post-order. Any idea on how we could do it? Here on the right side of the figure is our new implementation of the insert and extract functions. I'm not sure you remember it, but these two functions provide us with an interface to modify the worklist. If you want, you can stop the video and then take a look into the worklist algorithm and the new implementation of the extract and insert functions. Now, we represent the worklist as the combination of two data structures, C and P. C is a list of nodes to be visited. P is a set of nodes that were removed from the worklist, but that need to be revisited due to something changing in the state of variables created by the constraint system. And so nodes are always inserted into P and are always removed from C. Then once we are done with C, once C is empty, We sort the nodes in P in reverse post order, and then we copy all these vertices into C and start iterations again. Let me show you how this approach works. We start with the list C empty and every vertex in the set P. We have 6 vertices, 1 per constraint. Upon starting, we move all the vertices in P to C. We solve x1, the first constraint at C. And that causes us to add x2 and x4 into P. That happens because x2 and x4 depend on x1, and when we evaluate x1, the state of the inset 1 had changed. Then we evaluate x2. At that point, the state of x2 changes, and that causes us to add x2 and x3 to the worklist. We evaluate x3, and again, there is a change of state, but no new elements added to P. Remember that P is a set, and then we repeat entries. Repeated entries, cannot really happen in a set. We keep removing nodes from C and evaluating their constraints until eventually P is empty. At that moment, provided that we have observed changes of state, we move P onto C again, and the whole process starts again. However, this time no state changes. We evaluate all the constraints in C, but all the insets remain the same. So eventually C and P become empty, and the algorithm terminates. And then we are done. So the beauty of the reverse post order is that it ensures that when we evaluate a node, most of its predecessors have been already evaluated. Indeed, if the dependence graph has no cycles, then the reverse post order is equivalent to topological ordering. We would be able to solve the constraints in a single iteration. But can you think about other potential ways to order the nodes? Let me show you a few of them, and then we will discuss why these other potentially intuitive approaches would not be very good. For instance, on the top of the figure, I'm showing you what happens if we use a DFS to sort out the nodes. In this case, we could visit x6 before we visit x2, but that's not good because x2 depends on x6. So a DFS wouldn't be a very nice ordering, and the reverse post order is actually the reverse of the DFS. Now imagine that we use a breadth-first search, like in the bottom. In this case, if I add a new node xz in gray in the figure, then we could visit x6 before we visited x2 again. So simple DFS and BFS usually keep more dependencies than reverse post order. And that was it for reverse post order. Next time we will see a few other optimizations that we can apply on the worklist algorithm, and then that's it.